Hi everyone, in this video we're going to start going through some anti-differentiation, or another word that you might hear used is integration. So the syllabus says that we need to be able to calculate antiderivatives of polynomial functions. So we know what a polynomial function is, a function with powers of x that are positive whole numbers. We've been doing derivatives of these functions, so this video is about doing antiderivatives and a few examples on that. So if you look at this situation here where we've got a whiteboard and we're doing a test on differentiation, on one side we've got the original function, on the other side we've got the answer. So we could do this test. I can see from the first one that we've got 10x squared is the answer, or sorry, 10x is the answer to the derivative. So the original function that we started off with, of course, was 5x squared. That's easy to fill in. The derivative is 12x, so we started off with something x squared plus 4. You can see the left hand side of the board's been rubbed out here. So let's think, if we were going to get 12x for the derivative, I reckon that you'd have to have 6 lots of x squared plus 4, and then the derivative would be 12x. So I'm kind of working backwards, so rather than going from here to here, I'm thinking, okay, if the derivative is 12x, what must the original function have been? Alright, so if the derivative is 7, what must the original function have been over here? The derivative of 3 is 0, so that's not going to, I'm not going to worry about that. I reckon if we had 7x for the original function, the derivative would end up being 7. Similarly for this one here, if the original function was 4x, the derivative would be 4. Now notice I could put any number I wanted there on the end, and the derivative would still be 4. If the original function is x squared plus 3, we'd end up with 2x plus 1, etc. You get the idea. We're going backwards. We're starting with a derivative, and we're doing the antiderivative, the function that when we differentiate it, we get that. Okay, so notice that when we do this antidifferentiation, we need a plus c on the end, because when we do the derivative of any constant term is just 0. So if we start off with the right hand side here, we could end up with anything in, like in this example here, if we had the derivative of 4, I could have 4x plus 1 for the antiderivative, 4x plus 2, 4x plus 10. The derivative of that is always going to be 4. So we do need to be adding a number, a constant there on the end to get this right. Graphically, you can see that if we move a graph up or down, the slope doesn't change. So if we've got a curve of like y equals x squared, and then we move it up c units, the derivative at that point is going to be exactly the same as what we originally started with. So, okay, here's the rule. The rule for doing antiderivatives is simple. You add 1 to the power and divide by that new power. So here's our polynomial function here, x to the power of n. Here's our antiderivative, or integral. This long symbol here, this is basically like a long S, and it means sum, and I'll explain more about that later, about the applications of what this actually means, but for now we're just going to work out some antiderivatives. So that's the rule. We add 1 to the power and divide by the new number, and not forgetting we need to add c. In these problems you might see the integral of x to the n dx, this thing right here. What that really means is we're doing it with respect to the variable x. Let's see some examples. So the antiderivative of x cubed, we add 1 to the power and divide by that new number, and we add c onto the end. 3x to the power of 4, we add 1 to the power, divide by that new number. This is easy. 7's a little bit trickier. We're thinking what function when we differentiate it gives 7. The answer is 7x. And for d, we've got a sum terms here. We've got 4x to the power of 4 over 4 plus 12x cubed over 3 minus 6x squared over 2 plus c for that one. Now in this case here, we would definitely want to simplify each of these terms here. So we ended up with that, and that's the answer for D. Example 2, if dy dx is 5 minus 9x squared, and when x equals 1, y equals 10, find y in terms of x and y when x equals minus 1. So a little bit more information here, we can actually find what that plus c is. So if we start with the derivative, the original function is just going to be the integral of 5 minus 9x squared. Okay? The integral undoes the derivative with respect to x. So add 1 to the power divided by the new number. So here we've got we've got 5x to the power of 0 here. So we add 1 to the power divided by the new number, we end up with 5x. That's one way you can kind of think of that. Minus 9x cubed over 3 plus c. So I'm going to simplify that. Just makes it easier to look at. Now we know that when x equals 1, y equals 10. That little bit of information is going to help us to find what c is. Okay, so I'm substituting in x equals 1 and y equals 10. That gives me 5 minus 3, 2 plus c, so I get c is equal to 8. So now I know y in terms of x. Y is 5x minus 3x cubed plus 8. So that's how you find y in terms of x, and then it wants us to find y when x is equal to minus 1. So that's just a matter of substituting x equals negative 1 into that expression there. So let's quickly do that. So when x is minus 1, and you really should write this step down. This is something that you could do on your calculator, but really we should be able to do this in our heads, right? Negative 5, negative 1 cubed is negative 1, so negative 3 times negative 1 is plus 3 plus 8. Negative 5 plus 3 is negative 2 plus 8 is equal to 6. Alright, so the curve also goes through the point negative 1, 6. Here's a more interesting problem where we're talking about the revenue raised from the sale of a certain number of units of a particular product. And this question here is giving us what we call the marginal revenue. So it's the rate of change of the revenue in dollars per unit. So we want to find Rx, the revenue in terms of x, and the total revenue resulting from the sale of 100 items. So to undo a derivative, we need to do this integration process, this anti-differentiation process. So if I kind of do it a little bit more formally here, we're integrating both sides, 50 minus x over 20, and what we're going to do is say that that's 50 minus x over 20 dx. So I've kind of put the dx over the other side. So these derivatives behave like fractions. They're actually very, very handy. So the integral of 1 with respect to the variable big R is just r. So that shows us that the way that we undo the integral here, undo a derivative, is just by integrating. So we end up with r. On the right hand side we get 50x minus x over 20. So this is minus, you could think of the top line as you add 1 to the power, divide by the new number, and just leave the divided by 20 there. Or it might just be simpler to think of that as 2 times 20, 40 plus c. Remember, we always have to add c. The question says the sale of 0 items results in 0 revenue. So the revenue is 0 when x is equal to 0. So that means c must be equal to 0. So we've now worked out what the revenue function is. It's just that. So the question then says, determine the total revenue resulting from the sale of 100 items. Okay. Oops. So this is when x is equal to 100. So this is definitely now in the calculator section where we want to get our calculator out, and that works out to 4,750.